Hi, my name is Consortium and I'm here to tell you about our project, CoACH. It involves 15 PhD fellows engaged in the development of advanced glasses, composites and ceramics for innovative applications. As an enthusiastic researcher at the beginning of our careers, the funding granted through the CoACH program allows us to work in state-of-the-art facilities and stimulating and multidisciplinary environment. The CoACH consortium is composed of 5 academic institutions and 10 private partners, all based in the European Union. The aim of a project like this is to train new material experts at the highest standards and to boost the interaction between academia and industry. The research topics are grouped in 3 main areas: health technologies, energy materials, and environmental friendly building materials. Let's have a look how we are doing so far.
I'm Paolo Petiscoa from Spain, and I am a Marie Curie Fellow within the European Training Network CoACH.
I'm currently doing a PhD in Materials Science and Technology at the Politecnico di Torino in Italy, where I'm carrying out research in the field of photonics. In this project, I fabricate innovative glasses and glass ceramics seeking to improve their luminescence properties. These newly developed materials could be used for photonic and biomedical applications. The Marie Curie grant has given me the opportunity to work together with researchers at both companies and academic institutions and to attend to international conferences and trainings.
Hello everybody, I'm Cristian Marro and I'm the early researcher too in this CoACH ETN project. I'm working in the work package 2 that consists in glasses, glass ceramics and composites for the energy production and ICT industries. In CoACH project, I'm developing a new sensor based on optical glass fiber in order to detect chemicals through the matrix of the reinforced polymer composites. As you can see, the sensors are embedded inside this polymer matrix, and they are really small, and for this reason they are non-invasive, and also they work with light. That means that they are fire safety, and also they are not susceptible for the electromagnetic fields.
Hi everybody, I am Hassan Javed and I am working at Politecnico di Torino, Italy as a Marie Curie Fellowship under the framework of CoACH project, and the topic of my research is mainly related to the synthesis and characterization of glass forming materials for solid oxide electrolysis cell. The topic on which I am working is mainly related to the development of glass cylinders which are used in the solid oxide electrolysis cell to provide any sort of electrical insulation as well as to avoid the mixing of different gases at different electrodes. Other than that, I am also working upon the development and deposition of ceramic coatings on the interconnects which are being used in the solid oxide electrolysis cell. The coatings are important in order to hinder the evaporation of the chromium from the crowfoil interconnect. So, and then after successful deposition of this material and after having the sealants properly, I will use them into the real stacks. I am working in the collaboration of Sunfire, which is located in the Dresden, and they are synthesizing solid oxide electrolysis cell as well as solid oxide fuel cell at the moment.
Ciao, I'm Francesca, one of the fellows of the CoACH group, and my project is based on the production and characterization of order mesoporous bioptic glass coating with antibacterial properties for biomedical application. Once that I produce the glass, it's fundamental to check the order mesoporosity of the structure, and this is possible thanks to the TM microscope. Thanks to the funding of European Union, I got the possibility to be trained in the use of this microscope, and during my experiment, I performed some analysis, and this is one of the pictures that I took of my sample. Here we can see that the order of the porosity and the pores are in the order of nanometers. This allows in the future work to introduce inside the pores drugs that can improve the properties of the coating. See you!
Hello, my name is Nicoletta Toniolo, and today I will show you how I make geopolymers. Starting from the raw material, glass waste and fly ash, we are mixing everything together with sodium hydroxide for 4 hours. After that, when the slurry is homogeneous, we can cast it in polyethylene molds. We are vibrating our material with a vortex to take out the bubbles. So after that, the geopolymer is ready and we can put it in the oven for the curing.
Hi, I'm Bhuvanesh Srinivasan, CoACH ESR6, hosted in Glasses and Ceramics Laboratory of University of Rennes in France. My project is focused on developing novel glasses, ceramics and polycrystalline materials, especially chalcogenides, for thermoelectric applications. Thermoelectrics is one of the fast-growing energy sectors and finds applications in power generation, refrigeration and many more. We prepare glasses and ceramics either by traditional milk quenching technique or by mechanical synthesis followed by fast plasma filtering for compaction. The thermoelectric performance of the synthesized materials are estimated by measuring their transport properties like carrier concentration, mobility, electrical conductivity, Seebeck and thermal conductivity. Some of these measurements are carried out at nanoforce thanks to our consortium. High resolution microscopy and electron diffraction are done to understand their properties at nanoscale. Besides experimental activities, we also work with theoretical simulations team in Rennes to perform some ab initio calculations and quantum simulations to understand the local environment and band structure of our glasses and crystalline materials. On a whole, pretty much happy to be a part of this multicultural CoACH family. You can follow our research and other recreational activities through our CoACH website and other social media pages. Thank you.
Hi, I'm Acacio Rincon. I'm working in the University of Padua. Here we are developing new material from wastes. One of the materials that we are doing is a glass foam that is apart from the normal bottles, because when we do the recycle of the bottles, there are some impurities and that fraction remains with no use. So we make the foam just by doing a suspension and adding some tensioactive on it. When the foam is done, we just dry it and put in the furnace. After this treatment, we have an isolation material that could be used for building. With the same technique, we also have developed some material with a copper slag or with municipal solid bottomers.
Hi everybody, welcome to the Institute of Physical Materials of Renault. My name is Alessandra Mazzini and my PhD study focuses on ceramics for solid oxide fuel cells and solid electrolysis cells. In this moment, I am dealing with the measurement of mechanical properties of these ceramics. So today I'm going to perform a 3-point bending test on the ceramics. Now I'm placing the sample on the rollers and I have to make sure that it's actually in the center. You can see the graph, the loading curve, so load versus displacement. The sample will undergo 2 loading and unloading cycles. This way, I will be allowed to estimate also the elastical properties, elastic constants, beside the fractional strength. Now the sample underwent both cycles and the test is going to fracture. Now the test is over.
Hi everybody, my name is Gianmarco Taveri and I'm working as a PhD candidate. My PhD project deals very much in production of materials like the synthesis of inorganic polymers that are called geopolymers. The geopolymers are made of aluminosilicates, but in my project I'm using waste materials like this one, fly ash. The fly ash is a normal byproduct from coal power plant, and we mix this aluminosilicate source with a solution of sodium hydroxide. We make a slurry, we mix it, mechanically mix it, and we cast it in a rubber mold. we make a curing at high temperature, relative high temperature, like for example 80 degrees, for at least 24 hours.
Hello there, my name is Sylvie Ivan, and I am ESR number 10 within the CoACH project. The focus of my work is on material behavior and degradation, specifically the acceleration of aging in glass fiber reinforced polymers, in order to put together a prediction methodology. This is being done through material fabrication and machining, mechanical performance characterization through quasi-static and creep testing, chemical exposure, and subsequent material analysis. The ultimate goal is to better understand the effects of exposure on these materials to various couplings of the following three factors: load, temperature, and chemical agents. This will in turn allow for better component design within the energy sector. If you want to learn more, feel free to contact us, and thank you for your time.
Hi everyone, my name is Matteo Calzini. I'm a materials engineer from Italy, and I'm working as Marie Curie PhD student at the Element Testing Facility in Itchen, UK. Here, I'm studying the accumulation and aging phenomena that affect composite materials when deployed in marine environment. This material really suffer when subjected to the combined effect of a high degree of moisture and elevated temperature. The development of suitable testing techniques is of critical importance when evaluating the effects of addressing the environment. Such conditions can also be used to accelerate the aging of the composites in order to foresee long-term performance. I'm also studying innovative coatings as hybrid liners to improve wear performances on polymer substrates and foams as thermal barriers. If you fancy finding out more about our project, please get in touch with us on our socials. And thanks for watching.
Hi, my name is Rodrieta Fiorastrilla. I'm involved in work package regarding healthcare technologies. Bacterial infections are a problem that are getting worse because of antimicrobial resistance. Because of this, I am developing an antibacterial coating which can be applied on different surfaces. For example, bioactive glasses, steel, or titanium, in order to expand the applications of such materials in fields like dental, orthopedic, or tissue engineering. I'm carrying out my research in a private company, so I'm in continuous contact with the industrial world. Thanks to this Marie Curie ITN action, I'm receiving training on different areas, from the use of research equipment up to entrepreneurship management.
Hello, my name is Francesco Gucci, I'm the ESR 13 and I'm hosted in nanoforce at the Queen Mary University of London. My project title is Development and Processing of Nanostructured Materials, including Thermoelectrics. So we use the device behind me, which is a spark plasma sintering device, to densify powder into pellets. Currently we are testing a newly developed technique, which is called flash sintering, to take advantage of an extremely high heating rate. Till now I reached 7,500 degrees per minute, and this can allow us to obtain new microstructure and improve the properties of the material. After we obtain a pellet, we can observe the microstructure and measure the thermoelectric properties in order to establish the efficiency of the material.
Hi, this is my material. It's silicon oxide carbide with graphene oxide composite. And here you can see we are doing the mapping, and here this is a graphene oxide layer in the silicon oxygen carbide matrix.
My name is Katarzyna Placha, and I'm a PhD researcher within the CoACH project. My research is mostly focused on modeling and constructing devices, including innovative joining of high-temperature thermoelectric devices. Although thermoelectric market demand is growing, development of suitable fabrication process of a thermoelectric device continues to present an important challenge. The fabrication of thermoelectric device involves several critical steps, starting from sintering of thermoelectric material by spark plasma sintering, the position of suitable diffusion barrier through electroplating, accurate machining of thermoelectric legs, and finally joining them with electrodes. Within CoACH project, we work on developing commercial high-temperature thermoelectric devices, starting from materials fabrication, joining, and final device encapsulation. Thank you for watching.